So thanks everyone for coming to the BSc PhD Colloquium. Today's speaker is Arnob Ghosh, who did his undergrad and master's degrees at Jodhpur University in India in electrical and computer engineering and electrical engineering, respectively. His research interests are in game theory, game theoretic, and economics approaches to wireless networking problems and wireless spectrum access issues. So without further ado, I'll let Arnob have the floor to introduce his talk.
Okay, thank you, Alex, and thanks for being present here. So am I audible at the back? Yeah, okay, fine. So I want to first rectify Alex. So I have only done my bachelor's in Jodhpur. I have done my master's in Penn. It's okay, fine. Okay, so this is a joint work with my advisor, Saswati. And so first, I will talk about the motivation behind the work. So as we are living in a world where there are all devices becoming smart. So you have smartphone, tablets, smart devices. So that is why the demand for mobile broadband is also increasing very fast. So recent studies suggest that the demand for mobile broadband will soon surpass the available wireless spectrum. So, but this scarcity is artificial. So, because largely these licensed bands are underutilized. So, why is it so? Because of the FCC's like static spectrum allocation. So, FCC generally allocates some spectrum to the service providers like AT&T, Verizon, or Sprint. And if this spectrum is not utilized at a time, so this means that this spectrum is like not being utilized, right? So these that's why the licensed bands are largely underutilized. So you can see from this figure, like mostly like the spectrum occupancy is hardly 50% for most of the bands, like. And this is for the scenario for two cities like Chicago and New York City, and in most of the bands the spectrum occupancy is less than 50%. So researchers are looking for alternative, and that is why the term like secondary spectrum access has been coined. So what is the secondary spectrum access? So suppose if you have primaries like service providers like AT&T, Verizon, and they have their licensed spectrum band. So when they have their ideal spectrum, that is the licensed bands are not utilized, they can lease it to some unlicensed users, or which is known as secondary users. So these secondary users can be end users like us who do not have any contract with the service provider like AT&T or Verizon, but they can opportunistically access the spectrum. Or this can be like local service provider or some content provider who does not have the infrastructure like the AT&T or Verizon, and they want to just sell their spectrum at a certain location. But it is not about the giving the ideal band to the secondary users. It is also about the incentive. So if the primaries do not have any incentive to participate in this kind of market, so they will not entertain this kind of secondary access. So to model this kind of incentives, we consider like a market-like thing, which is called a secondary market. So here at each time slot, each primary will offer its channel to the secondaries in exchange of some money. And the channel of a primary also offers some transmission rate because of the noise of the fading, and also like usage level of the primary users, which corresponds to the interference that the secondary users will get. So we discretize the transmission rate into different states belonging from 0 to n, and lower index means that the transmission rate is low. And for some transmission, you should have some kind of minimum rate, right? So at state 0, the transmission rate is very low. So that means that if the channel at certain time that state is 0, that means that the primaries cannot sell its channel, or in other words, secondary will not prefer that channel. As this kind of all the transmission, the dependence variable like the usage level, the fading, noise level, all these evolve randomly. So that is why the states also evolve randomly. So what are the buyers and sellers in this kind of market? So you have you have primary which selects the price depending on the channel state, and but But in this kind of setting, a primary does not know about the channel states of its competitors. It knows the channel state of its own, but it does not know its competitor. So suppose at the market, AT&T knows its own channel state, but it does not know its competitor, say Verizon or Sprint. But it has some kind of belief or probability distributions over the states. So we made an assumption like the probability distributions are the probability distributions are IID. That is, all the primaries have the same belief. And we also made a specific assumption to avoid the interference at a location, that at a certain location a primary will only allow one secondary to use this channel. So a secondary user decision is very simple. It will just go to the market and will select a channel depending on the price and transmission rate. Right. But in order to model the preference order of secondary, we consider some kind of utility function or penalty function. So as the term suggests, the secondary will prefer a channel with low penalty. So this penalty function is strictly increasing in price and decreasing in transmission rate. The higher transmission rate should incur high utility. So this means that the penalty should be low. And the highest acceptable penalty is V. So we consider a wide range of functions that and mainly which has some kind of additive property, like if at channel state I, the penalty will be some price minus some transmission rate. So for simplicity, you can consider the penalty penalty at price X at channel state I, says X minus I. And also some other complicated functions are also considered. Okay. So now as there are a lot of primaries, so it is an oligopoly market because there are competition among multiple primaries. And also, but there are some special features about the secondary oligopoly market compared to the economic market. So why is it so? The first is that there is uncertainty in competition. So as the primary does not know the channel states of its competitors, right? So suppose AT&T knows that my competitor Verizon has very high quality channel, so I should price my channel at very low price, right? But if it knows that okay, my competitors have very low quality channel or it does not have any channel to sell, so I will probably raise my price because there is no competition in the market. So it leads to a challenging problem because there is a dilemma whether a primary should choose the high price or the low price. And also, in the secondary, in the spectrum market, there is interference. So, a primary, if signals at adjacent locations cannot be transmitted simultaneously because of the interference. So a primary can sell its channel to the locations which do not interfere. So this is known as spatial reuse. So a primary must have to select a set of locations which do not interfere with each other. So we like to solve this whole problem, but first we look at the single location pricing where there is no spatial reuse. So is there any question before we go into the model of the game? Yeah.
The assumption that the computers don't know the quality of each other's channels. The channels are just random frequency spectrum. Can they measure the quality?
So as an AT&T, I can measure my quality. I cannot measure my competitor's quality. Because it operates in different frequencies, right? Okay, so we are first consider the single location pricing strategy. So why we look at it? Because first of all, it will give some nice results and which we use it for solving the joint decision problem. And also it has some independent interest because if you have some kind of uncertainty in competition in a market, these results can be useful. So here the primary owns a channel only at single location, so there is no special reuse. But primary needs to select its strategy, that is, it needs to select its price. But there is a one-to-one function between the price and penalty. So we can consider instead of price, the penalty is selecting penalty. Sorry, primary is selecting penalty. So we consider like primary select some penalty distribution. This can be a pure strategy or mixed strategy. That means that it can be deterministic or it can randomize among the penalty values. So but first of all, looking into the solution of the problem, we first define what is the payoff of a primary. So payoff of a primary at penalty x is like fgx minus c, some function. Fg is the inverse of the penalty function, and c is some transaction cost. If the primary is allowed, if the primary can sell its channel, then obviously its payoff will be fgx minus c. But if it cannot, its payoff will be 0. And we seek to obtain a Nash equilibrium. So what is a Nash equilibrium? A Nash equilibrium is a strategy profile where no primary can improve its expected profit unilaterally deviating from its strategy profile. And what is a symmetric any? Like this distribution will be the same for every primary. Then it will be like symmetric any. So this is the first result for the single location pricing strategy. So there exists a unique Nash equilibrium, and in the Nash equilibrium, like at channel state I, a primary selects penalty from the interval like Li to Li minus 1. And these intervals are ordered. So suppose at channel state N, primary selects a penalty from Ln to Ln minus 1. At channel state N minus 1, it will select from Ln minus 1 to Ln minus 2 and so on. So an algorithm has also been provided to compute this Nash equilibrium. Okay, so what are the properties of this Nash equilibrium? So first is that this Nash equilibrium is symmetric, right? There is no asymmetric any. And also the next thing is that there are no pure any strategy profile. So that means that there is no deterministic any, and this is a like purely mixed strategy. And another important thing is that which may not be very intuitive is that a primary selects lower penalty when the channel state is high. So you can see like at channel state N, it is selecting from penalty Ln to Ln minus 1. At channel state N minus 1, it is selecting from Ln minus 1 to Ln minus 2, and Ln minus 2 is greater than Ln, right? So a primary will try to price the channel at different transmission rates such that the high quality channel will always be preferable to the secondaries compared to the lower quality channel. So this negates the popular belief that the channel should be priced in such a way that each channel state will be equally preferable to the secondaries, right? But this is not about price; it is about penalty. So okay, so we have to map this penalty to the price. But so even if the penalty is lower, the price can be higher when the channel quality is high. But it may happen that the primary can select low price when the channel quality is high. But when the competition for the high quality channel is very intense, a primary may select low price for the high quality channel. And also the support sets of the penalty distributions are contiguous. So to give a like flavor, like what would be like the penalties and what would be like the distribution. So consider a simple example. So there are 21 number of primaries and 10 secondaries, and the channel state is 3, right? So here like at L1, that is at channel state 1, the primary will select a penalty from some value to 22.864 to 100. At channel state 2, it will select from 17.345 to 22.864. At channel state 3, it selects from 17.266 to 17.345. Okay. So this is for for the single location pricing strategy, the penalty distribution functions. And what about the efficiency? So what is the efficiency in this setting? Like the efficiency is the expected the ratio of the expected payoff at any strategy, and because it is a like non cooperative game, like primaries are competing with each other. So what will happen if the primaries will cooperate with each other and gain some like optimal payoff? So what is the ratio between this expected payoff at any and the payoff that the primary would have obtained if all the primaries would have colluded? So we can present the result in terms of ratio of the demand and the number of primaries, that is the supply. So if the number of secondaries and number of primaries is below a threshold, then the efficiency will tend to 0. And if the number of secondaries and the number of primaries is greater than T2, then the efficiency tends to 1. So why is it so? If the demand is very small, then that means that there is a lot of competition. So the primaries will try to capture this low demand. So this means that primary have to select low price. So this brings the efficiency towards 0, because if primaries would have colluded, they would still select very high price because there is no competition. But if the demand is becoming higher, then the competition becomes low. So that means that the primaries can select higher prices because there are higher demand. So so the primaries know that, okay, some secondary may buy my channel, even if I set high price. So that's why the efficiency becoming 1. Okay, so this curve shows the payoff function as you increase the M. So as you can see, when the number of secondary is very small, like when it's less than F, all the payoffs are or almost 0. But as the number of secondaries are increasing, the payoffs becoming positive. So when the M is like in the middle range, like 15 to 5, so it's like the challenge states, the payoff at challenge state 1, 2 are 0, but the challenge states at 3 is high. So this is the P3, which is high, is positive. But when the M becoming higher, the payoff at channel state 2 becoming positive. And when M is sufficiently large, so all the payoffs are becoming positive. Okay, so but we have discretized the transmission rate into some discrete setting, like n is for finite n. But what will happen if the n becomes large? Because in reality we have continuous transmission rate, so we should have like very high n to model this kind of continuous transmission rate. So as you can see, when n is becoming very large, all this L1, L2, Ln all converging. Like L1 is converging to the highest possible penalty, and Ln converging to some value which is lower than V1. And this convergence rate is higher for these Lns compared to L1. So what does this mean? That even if for finite n the distribution functions are mixed strategy, that the primaries are selecting from using some distribution function, but when n is becoming large, they will selecting a pure strategy. So they for a given transmission rate, they will select a deterministic price. So that is very interesting. Okay, so now we will look into for the case when a primary owns a channel over multiple locations. So if you have any question, this is a good point to ask for single. Yeah.
You said that there is no asymmetric equilibrium for this symmetric set. So what about asymmetric equilibrium for asymmetric set?
So yeah, we are not considered in asymmetric setting.
So and the second is also considered to be the same, right? All the secondaries are the same and all the primaries are the same.
Sorry, what result?
So the secondaries all
considered
to be the same.
Yeah, secondaries are homogeneous. All the secondaries are same. All secondaries have the same preference order. Yeah. Yeah.
These secondary markets are already being implemented?
No, it is not being implemented yet. Yeah, that is a good question. Yeah, it is not being implemented yet.
If they're, are they allowed to sell by FCC, are they allowed to sell their spectrum to the secondary clients?
No, so not yet. So this is secondary market is not yet in place. But what are they doing is that they are using the cognitive radio network, right? So using cognitive radio network, they can like send channel using like opportunistic manner. It is not in place like they are for this kind of market, but using cognitive radio network, you can send signal using in opportunistic spectrum manner.
So if it's going to be regularized, don't you think that FCC would require them to announce their, because if I want to buy something, I want to know what I'm buying. So FCC would require require them to announce the quality of their channel.
Yeah.
So then, how would it affect the equilibrium if they're announcing their? I mean, then it won't be an imperfect information.
No, but so we are considering that the belief functions is same, right? This result is from the belief functions are the same. So even if FCC allows the primaries to announce their qualities, so as a competitor, I do not know what is the quality of my competitor at the time of being announcing.
It's not announcing. FCC would require them to announce the truth because if I'm a secondary buyer, I don't know what I'm buying.
Yeah.
So I'm not sure, but I think it seems the same for power grid. You have to tell what you're selling.
Yeah. So sorry. Sorry. So I don't get the question. So what is your question?
FCC won't require the primaries to announce the quality of the channel that you're selling.
Yeah.
Then it's not a belief function. Then they know they're announcing.
No, but before the announcing, they do not know. Like, so suppose I am a secondary, right? I am trying to buy the channel, so I will have some kind of transmission rate for each primary for each primaries channel, right? So I will see the prices and the transmission rate, then I will consider buying. So primaries will first set the price, okay, and I am secondary, I go to the market and okay, I will see the transmission rate and then I will buy. This answers your question?
Yes. So I think what you're asking is that so the problem is that in wireless settings we don't know the quality for them, right? So what the primaries can do is to code or announce their distribution, right, for the quality, which is the same as this model. So they all have distribution.
Or instead of distribution, you can have some mean value, mean expected value. Okay, so we go to the second setting, like when the region consists of multiple locations. So here we consider here we also break down into more settings. So first is the region consists of few locations. So here the important assumption is that the transmission rate will be similar at each location. And the second setting, we consider the region consists of very large number of locations, possibly infinite. And so the transmission rate will be largely uncorrelated at different locations. Okay, so first is region consists of few but multiple locations. Okay, so a primary owns a channel over multiple locations, so we make the assumption that the secondaries need not be the same at each node, but the probability distribution of secondaries must be identical at each node. Okay, so as you know that the signals at adjacent locations cannot be transmitted simultaneously because of the interference. So a primary needs to select a set of locations which do not interfere with each other, which is known as independent set. And the transmission rate is assumed to be the same at each node, and channel state is also the same at each node because the transmission rate is the same. So the possible channel states over the network are 0 to 1 to n. So what is the decision problem for primary? For each channel state j equals to 1 to n, a primary must select an independent set of nodes and a price at each node of the independent set, right? Okay, so we often model this interference using some graph, which is known as conflict graph. So conflict graph is a graph where an edge exists between two nodes if and only if the transmission rate transmission at the corresponding nodes interfere with each other. So you can see here these two neighboring locations interfere with each other. So this gives a linear conflict graph. Okay, so to motivate, there are more conflict graphs. So you can consider these 1, 2, 3, 4 are like the wireless access points, and they interfere with each other. So this gives a complete graph, which is also known as grid graph. And here these wireless access points 2 and 4 do not interfere with each other, and 1 and 3 do not interfere with each other. So there is no edge between 1 and 3 and 2 and 4. So what are the independent sets of this graph? So you can see here 1, 3 is an independent set, 2, 4 is an independent set. But here the independent set is only one node, like 1, 2, 3, or 4, because if you include another node, it will interfere with each other. Okay. So we look into some specific conflict graphs which are known as mean valid graphs. So in this mean valid graph, the set of nodes can be partitioned in D maximal independent sets, right? So what is the maximal independent set? So it is an independent set. You cannot add another node and being independent. So but the most important thing is that the conflict graphs that are seen that arise in the practice are mostly mean valid graphs. You can see linear graph which is a mean valid graph with D equals to 2. So it is a bipartite graph. And if you have a 2 and 3 dimensional grid graph, which are mostly a bipartite or 4-partite or 8-partite graph. And cellular network with hexagonal cells, which is also a mean valid graph, which is a tripartite graph. Okay, so what is the primary strategy here? So primary strategy has to select independent set, right? So its strategy is like probability mass function over the independent sets and penalty distribution at each node of the independent set at each channel state, right? But if a primary select, so primary wants to maximize its expected payoff, right? So if it will try to select. It will try to sell its channel at most of the location as possible. So if it selects the independent set with maximum cardinality, like there will be huge competition because all wants to sell its channel to the maximum independent set, right? So a primary can gain more payoff by selecting an independent set which is of not maximum cardinality. And also the important question is how should a primary randomize among independent sets at different channel states. Okay, so what is the payoff of a primary here? The payoff of a primary of an independent set is the sum of the payoffs at each node of the independent set, right? And again we seek to obtain the Nash equilibrium strategy. But the first result is that we have like unique any for the single location case, but here there are multiple asymmetric any's. Okay, so and also like in a single location case there was no asymmetric any, but here there can be multiple asymmetric any's. So what are these two asymmetric any's? So consider like there are this is a linear graph with only 2 nodes, right? So suppose primary they divide the nodes among themselves. So there are 2 primaries, one will choose node 1 and the other will choose node 2. So there is no competition at a node, right? So primary will select the highest penalty at node 1 and primary 2 will select the highest penalty at node 2. So you can interchange this, right? So these are the 2 asymmetric any's. But in this game is symmetric, like all the payoffs are similar and the primaries also have the same belief. So in the symmetric game, it is difficult to implement asymmetric any's, because if suppose there are 2 primaries and they are selecting strategy S1 and S2, if this is an any, if they can interchange their strategy like S2 and S1, it will also be an any because of the symmetric nature of the game. So you need to like a primary needs to know what other primaries is selecting. Like I will choose my strategy S1 if other is selecting S2. If I will choose my strategy S2 if other is selecting S1. So, but it is a non-cooperative game. So you cannot like you should not like tell other people what am I doing, right? So that's why we focus on symmetric any's. Because here the strategy will be identical for these primary. Okay, so the main result in the symmetric game is that the pricing strategy. The pricing strategy can be obtained once we know the independent set selection strategy. So why is it? Because probability that a channel is offered at a node is completely specified on the independent set selection probabilities. Independent set selection probabilities can specify the node selection probabilities. So once we know the node selection probabilities or the probability with which a channel is available at a node, we can come up with the pricing strategy, as we have seen in the first section of the slides. Okay, so what is the consequence is that we can only focus on the independent set selection strategy, but still it is a very hard NPR problem to obtain an any because it is a combinatorial problem, and the number of independent sets also grows exponentially with the number of nodes. So that's why the computation and storage requirement also grow exponentially. So how can I solve this problem? Okay, so we will use the important property of invalid graph. That is a d-partite graph, right? So if we have an any which only selects among these I1 to ID, so we only need to store d independent sets, right? The storage requirement does not exponentially grows with the number of nodes, but it only scales with d, right? So it is only scales with like at most linearly with the nodes. So, and the result is that, okay, we look into that, okay, and what is that? Like, is there any or something like that? Yeah, so there exists a symmetric any strategy profile in a mean valid graph where a primary only selects independent sets among I1 to ID with positive probability. Again, we have explicitly computed this any strategy profile. Okay, so what are the key properties of this any strategy? So first is that it is a threshold type strategy. So at a channel state, primary only selects an independent set whose cardinality is like greater than a threshold, certain threshold, and the threshold is a non-decreasing function of the quality of the channel. So for higher quality of the channel, a primary only selects very selected independent sets which have very high cardinalities. As the channel quality gets lower, it will try to randomize over the other independent sets which have lower cardinalities. And so this means that it may happen that at some locations the secondary users may only get access to channel of lower quality or may not even access to the channel of the primary. So there is some social inequality in this game, right? In the multiple locations game. Okay, so what about the uniqueness? So as we have seen, like in the setting where there is only single location, there is a unique any. But here the any may not be unique. Like in the symmetric any may not be unique. As we have seen, the any's are not unique as we have asymmetric any's. But a symmetric any also may not be unique because the partitions of the mean valid graph may not be unique. So here you have two sets of partitions, right? So if we select any at each set of partition, it will give rise to two different any's. Okay, so this is a problem because if I don't know what my competitor is selecting, so if these two any strategy profile give rise to two different strategy or the probability of node selection probabilities are different, so I have to communicate with my competitor what are the partition that I am selecting, right? But this is not feasible in the non-cooperative game. But we find that, okay, even if irrespective of the partition that my competitor is selecting, it will all lead to the same node selection probability. So as the node selection probability is the essential part for selecting my pricing strategy, and the payoff, so any strategy profiles are functionally unique. So it will give rise to the same pricing strategy at each node. So we do not need to communicate with my competitors for what partitions we are selecting. We also get a stronger result for special class of graphs, like if the confit graph is linear, then there is no the symmetric any is unique, and thus in the symmetric any, the primary will only select independent sets from the I1 to ID. Okay, so what about the efficiency in this setting? So as we can see, as we increase the number of secondaries, the efficiency increases because as the demand increases, the competition becomes lower. So that means that primaries can select a higher independent sets and the independent sets of higher cardinalities and higher prices. So that's why the efficiency increases. Okay. So do you have any question in this setting? Oh, sorry. Okay, so we look into the region when it consists of very large number of locations. Okay, so here as the locations are large, we cannot say that the transmission rate will be the same over the region, right? So the transmission rates can be different, and that's why the channel state can be different. So we should have some kind of channel state vector which denotes the channel state at each location for a channel. And again, a primary must select a set of non-interfering locations where the channel is available. So a primary must have to sell a channel which is available for sale. So it has to select a set of locations among the locations where the channel is available to sell its channel, right?
Sorry. So the
Yeah.
number of secondaries in each location is the same for all locations? Or?
Yeah, so the number of so we assume that the number of secondaries are it may not be the same, but the probability distribution must be identical.
For distribution of?
The distribution of the secondaries.
But did you consider distribution of secondaries?
So we can consider like the distribution of the demand. Demand may be uncertain.
Oh.
Okay, so here as I have told, like when there is a channel state vector J, like you must select among the nodes where the channel is available. So if this is the overall config graph G, but at channel state J, which has like the channel is available only the first three nodes, 1, 2, 3. So this is the config graph representing the channel state vector J. So this is Gj. So you must select an independent set among this graph to sell your channel. So, but this setting is very complicated because a primary needs to select an independent set for every possible channel state vector J, and a primary also does not know its competitor's channel state vectors. So if I have the channel state vector J, my competitor may have a different channel state vector, say J1. So my competitor may be selecting an independent set from completely different config graph from me. So to simplify this setting, we assume that the n is equals to 1. So this means that the channel is either available or not available for sale at a given location. But it's still a hard problem to solve because the strategy space scales exponentially with the number of nodes. So the strategy space will be 2 to the power v, because at a given node the channel may be 0 or 1. Okay, so regarding the channel statistics, we assume that the channel is at state 1 at a given location with probability q independent of the channel status at other locations. So this is channel state vectors are IID, but we also consider some kind of correlation among the channel states at different locations, but it is very technical, and you can find it in the paper. But for time being, you can consider the channel states are IID, that is at each location the channel is in state 1 with probability q. Okay, so what is the strategy of a primary in this setting? At channel state vector J, a primary needs to select an independent set in Gj, and the price at every node of the independent set in Gj. And also, what is the payoff? The payoff is the same, that the payoff over an independent set is the sum of the expected payoff at every node in the independent set. And again, we seek to obtain the Nash equilibrium. Okay, but when we see that when the graph is finite, we have like a mean valid graph is the like more prominent one. Like most of the graphs are mean valid. But when we increase the number of locations, so we are looking at the infinite graph, they have some symmetric structure, and which is known as the node symmetric graph. So what is a node symmetric graph? You can find a formal definition in any textbook. But here informally, like the nodes are equivalent and the graph looks the same from each node. So you can have some kind of example, like if you can see infinite square graph. So this is like extended to infinity, and you can see like for every node the graph looks the same. This is same for the infinite linear graph, or this is same for the infinite triangular graph. So So remarkably, when we like increase the number of locations to the infinity, this symmetric structure comes up, and the most of the complete graphs become like node symmetric graphs, like infinite linear graph, infinite square graph, infinite grid graph. And to be noted, like the finite counterparts of above graphs are also mean valid, but it may not be the node symmetric. But when you increase to the infinity, these graphs become node symmetric. Okay, so there are also some finite node symmetric graphs like cyclic graphs or complete graphs or cubic graphs, but we show results for the node symmetric graphs irrespective of the size. It may be finite or infinite. Okay, so again there are multiple asymmetric NEs, and multiple asymmetric NEs can be present for infinite graphs. I am not showing it because of I am slightly running out of time. But we focus on again symmetric NEs because it is very hard to implement asymmetric NE, as I have mentioned before. Okay, so again we have a separation result. The pricing strategy, we can have the joint decision problem can be separated by solving the independent set selection strategy and the pricing strategy separately. So the separation results extends to the general setting. So again the consequence is that we can only focus on independent set selection strategy. But it is still a hard problem to solve because the number of independent sets grows exponentially, and that's why the computation and storage requirement also grow exponentially. Okay, but we find that at a given channel state vector J, a primary randomizes equally among the maximum independent sets of Gj. So this is an like any. So if suppose there is a channel state vector J, and you have the complete graph Gj, then if only randomizes equally among the maximum independent sets. So I should have added another line is that this is an any. This is an any strategy profile. So if you just still randomizes equally among the maximum independent sets, so then this becomes an any. So the good thing is that the primary only needs to enumerate the maximum independent sets in this setting. Okay, so what are the properties of any? So a primary always selects a maximum independent set. So, but if you can see in the previous setting, a primary may select an independent set which is not maximum. A primary is selecting an independent set which is greater than a threshold, but it may not be the maximum one, right? So when you are extending the number of nodes to infinity, the primary only selects an independent set which is the maximum one. And primary offers this channel at every location with equal probability. As we can see in the previous setting, like a primary only may never offer its channel at some locations. But when we increasing the number of nodes to the infinity, a primary always like selects every location with the same probability. And that is why the expected payoff at every node is the same. So intuitively we can explain this thing because the graph becomes the node symmetric graph, so each node becomes equivalent. So there is no need to like prioritize one node over others. And what about the uniqueness of the symmetric NE? Again, the symmetric NE is not unique in node symmetric graph, but it is not even unique in the linear graphs. As we have seen in the setting when there is like few locations and the channel state is the same across the network, there is an unique NE in the linear graph. But this property does not extend to this setting. Okay, so as we have seen, like a primary needs to select a maximum independent sets, but the maximum independent sets can grow exponentially with the number of nodes, right? But at a given channel state vector J, the complete graph is like random because it depends on the channel state vector J, which is completely random. So maximum independent sets can be computed in each component in parallelly, and then a primary can select its strategy in each such component. So the main important thing is what should be the component size, which will bound the computational time. So we find that the average component size is an infinite size graph depends on the Q, the probability which the channel is available, and the degree of the node. So, but if Q becomes higher, so this component size can become very large, right? So this means that your computation computational time can also be large. But so Q cannot be controlled. It comes with the data. So you cannot control your channel state or your transmission rate of the primary users, but because they are your customers, right? So you cannot control Q. But a primary can, however, randomly sample a node with probability P, and can only sell its channel among the sampled nodes. So what are the advantage of this? The first is that the average computational time is now PQ times this. So if you can lower P, you can manage the computational time because the computation cost. So the computation cost also decreases, and also for being a channel state, to offer a channel state, you also have to estimate and measure the channel state at each location. But if you are sampling randomly, you do not have to measure this channel state at every location. You can only measure at the sampled nodes. So the estimation measurement cost also decreases. And this random sampling is also an any strategy profile. This can be shown. But the disadvantage is that a primary can potentially sell its channel at fewer locations, because it is sampling some of the locations. It is not offering a channel at all the locations. Okay, so this figure shows the component size with respect to PQ. As you can see, when the PQ exceeds the threshold, the component size increases exponentially. Okay, and the component size of a square graph is higher compared to the linear graph, because the nodes in the square graph is degree of a node in a square graph is higher compared to the linear graph. Okay, so we come to the last part. So what are the so I will just conclude here by summarizing what are the important results in your analysis. The first is that a primary always selects lower penalty for higher quality channel in the single location game. The any is always unique, but the any may not be unique in the multiple locations game. But the good thing is that in the multiple location game, the joint decision problem of selecting independent sets and pricing strategy can be decomposed by selecting independent set and prices separately. And the any in the multiple location is a threshold type strategy. When the channel state is the same, a primary selects independent set with cardinality is greater than the threshold. This may not be the maximum one, but when the region consists of large location, a primary always selects the maximum independent set. And also when the market is over small region, a primary may never offer its channel at location, but the good thing is that when the region becomes large and the number of nodes become almost infinity, like these secondaries at each location have equal probability to get access to the spectrum. And when the ratio of secondaries and primaries increases, the efficiency of the any solution also increases. But there are some few works to be done. Like the first is as I mentioned, the secondaries are the homogeneous one. So what will happen when the secondaries become heterogeneous? And also the characterization of any for general n when the number of locations are large. We only have results for when n equals to 1. So what will happen if we increase the n? So okay, so these are the results that should be done. Okay, thank you.
We have time for a few questions.
Yeah.
When you say not symmetric, you mean vertex transitive or is it
Vertex transitive, yeah. No, sorry.
Any other questions?
In practice,
Yeah.
how many nodes?
So in the initial stage of deployment, you can see like very few, like the market will be over very few locations, like 10, 20, 25. But as it increases, like 50, 100, 200, so it is more be like going to the node symmetric graphs. So it all depends on the growth of the secondary market, how it operates.
So the question, so these results that for large graphs measure have these sort of homogeneous policies. And that has to do more with the regular assumption than with the size. Right? You know?
Sorry?
With the assumption that the graph is going to be some kind of regular graph, than rather with the size. Right? So the size is just a way to get to the regularity assumption. But the result is based on the regularity rather than the size. Right?
Yeah, so you are talking about this, the results of the when they are equaling among the nodes, right? And then, it is about the regular graphs. Yeah, you are right about that thing. Yeah, but the main thing is that when the size becomes infinite, the commonly observed graphs become that kind of regular graphs. Yeah, you're right. Yeah.